So I've been working on computational imaging for about 30 years. One of the first things that I did when we started working on computational imaging was to think, could we get rid of lenses? Could we just measure the field or measure the mutual coherence directly and then form images without the use of lenses? And so we started working on the rotational shear interferometer. And I worked with rotational shear interferometers for about 10 years. And we were always looking at could we, for example, image point targets better with a rotational shear interferometer than with a focal system? Or could we isolate pairs of point targets better? That work, for me, culminated in this paper, written about 20 years ago, where we compared imaging with a focal telescope and with a RSI. The plots shown over here on the right at the top show the estimation of the intensity of a pair of point sources with an RSI and with a telescope. And these plots up here are using linear methods, Fourier methods, to estimate the intensity. And these plots down here are using a nonlinear estimator. This plot is for a model RSI, and this plot is for the telescope. And as you see, the telescope does a little bit better, about a factor of 2 better. That had to do with an assumption we made that the telescope was better at collecting light. That assumption was wrong. Lots of things about this paper were wrong, and I really regret that we didn't pay more attention to the science when we wrote this paper. The plot at the bottom shows estimation of the position of the 2-point targets. Again, these plots are using linear methods, and these plots are using nonlinear methods. And again, the telescope is a little bit better. And what you see is that we're able to estimate to around 1/10 of a pixel with the telescope, and somewhere within a factor of 2 worse than that with the RSI. So better than 1 pixel estimation of the position of the point source, but only when the point sources are well separated. And when you go here where the point sources are separated by less than a resolution element, we were unable to get a good estimate of the position of the point sources. Computational imaging is really about attention to detail. What I hope you get from this series of lectures is that if we model systems carefully, we can turn what you might think of as noise or uncertainty into signal and get better estimates. We saw that in chapters 5 and 6 when we looked at, for example, the quadratic terms in coherent imaging, which for many years people just ignored, but it turned out to be critical in creating synthetic aperture imaging and tychographic imaging systems, and have revolutionized coherent imaging. Here with imaging of incoherent sources, it turns out that careful attention to the details of the imaging system and the forward model can allow you to get better estimates than what you would get with a normal focal system. For the RSI, this was shown 13 years after this paper in the work of Nair and Sang. And what they did was build a Mach-Zehnder format of an RSI where you have a symmetric channel where most of the intensity from the RSI is passing through, and a asymmetric channel where the goal is to null the interferometer. And what Nair and Sang showed was that for the Fisher information, for the antisymmetric channel goes to 1 in this units of the width of the source as the separation between the 2 point sources goes to 0. And what that means is that even as the separation between the 2 point sources goes to 0, if you integrate long enough, you can get a good estimate of the separation between the 2 point sources. And as we'll see in today's episode, you may be able to estimate the position of the 2 point sources to 1/1000th or better of the width of the nominal PSF of the imaging system. That earlier paper that I showed you, for me, led me to stop working on RSIs 20 years ago. That was a mistake. In computational imaging, we need to focus on details and really understand the physics of what's going on. And sometimes we'll be then surprised by the data that we can get out of a system by careful analysis. So let's get into seeing what that means for estimation of the separation between 2-point targets. Computational imaging. Episode 45, the Rayleigh Criterion. Today's episode uses code that's on the GitHub site that goes with these lectures and with the course text. We're under the Computational Imaging GitHub site, Chapter 7, Coherence Imaging, and we're looking at Fisher information of 2 points as a notebook. One of the things that the notebook plots is the response that we get on two different instruments. One is a focal instrument that has a Gaussian impulse response. So it focuses a remote point source to a Gaussian focus spot. And then the other one is a rotational shear interferometer imaging the same sources. Now, here we're showing the response of the instrument for 2-point targets at various amounts of separation. Here at the bottom, the separation is 0. And so for the Gaussian response, we just see the Gaussian response of a single impulse response. And so this would be the overall width of the underlying Gaussian. On the right, we're seeing the output of the RSI. Now, if an RSI is pointing directly at a point source, we can align the RSI, if it's looking at a plane wave, we can align it to cancel the plane wave on one of the arms, so we get 0 output on the arm of the RSI. Here we're assuming that the RSI points at the midpoint of the 2-point targets. So if the targets are exactly on top of each other, it's pointing directly at the target. As the targets are separated, point at the midpoint, which would give us the least output on the arms of the RSI. Still gives an output because we have this low frequency cosine function that we would see from each of the point targets that are separated from the origin by some small amount. On the right hand side, the x-axis is in units of the width of the Gaussian impulse response. So this is small. This is on the order of, lambda f number for a focal system would be the units of the left-hand side of the Gaussian plot. The right-hand side, this is over the full aperture. So this is from minus 0.5 of the aperture radius to plus 0.5 of the aperture radius. So over a much larger area. And if we're pointed directly at the point target over the full aperture, we would get 0 output on RSI. And as we go to more and more separation, we start to see this cosinusoidal pattern. But the cosinusoidal pattern is at low frequency because the targets are as close to the origin as possible by aligning at their midpoint. So we want to compare our ability to estimate the separation of the point targets from these two different information sources. We're going to use Fisher information to do this. You'll recall that we discussed Fisher information back in episode 10, where we looked at our ability, for example, to estimate the centroid of a single point target. And here again, we had a Gaussian impulse response, and we showed that for Poisson noise, the Fisher information takes this form of the derivative of the response of the signal with respect to the hidden parameter squared divided by the impulse response, and we would integrate this over the full range of measurements, and that gives us the Fisher information relative to this parameter. In this case, the parameter is the mean position of the point target x naught. And back in episode 10, we showed that the Fisher information would go like the total integrated energy I naught divided by the variance of the Gaussian, so that the Kramer-Rao lower bound for estimation of the position of the point target would be the width of the impulse response squared divided by I naught. And then if we take the standard deviation that goes with that, we would find that we could estimate the target to something that would be proportional to the width of the impulse response divided by the square root of I naught, which would be the square root of the number of photons. So if we integrate a lot of photons, then we could estimate the centroid of this point target to much less than the width of the Gaussian impulse response. And as talked about back in that episode, this is used, among other things, for single molecule microscopy, where people, as a very standard practice now, are able to estimate the position of the emitting source to much less than lambda f number. Okay, so that's back in the past. This current notebook looks at the information for estimation of a spot, but now we have two spots. So we have our impulse response is the impulse response for each of 2-point targets, and we're assuming that we would like to know the mean position of the point targets and their separation. And so this is the impulse response due to one of the point targets, which would be at x bar minus delta, and the other point target is x bar plus delta. So x bar is their mean position, and this 2 delta is the separation between the 2-point targets. We can evaluate the Fisher information using exactly the same formula as we used in episode 10. We take the derivative to each one of the with respect to each one of the unknown parameters, and we can build now the Fisher information matrix. The terms take this form. Now it happens here that the mutual information of the mean position and delta is 0 in this case because the one function is even, one function is odd, and so that I of x bar delta integrates to 0, so the Fisher information is diagonal, that we have a separate Fisher information for the mean position and the separation of the 2 point targets. We can look at this Fisher information as a function of x bar and the Fisher information for x bar and delta as a function of delta. And what you see is something like this. And the interesting thing is that as delta, the separation between the 2 point targets, goes to 0, the Fisher information goes to 0. So here the Fisher information when delta is 0 is 0. And so, of course, if delta is not small but not 0, the Fisher information is non-zero, so we can still estimate delta. But it turns out that the Kramer-Out lower bound will be much greater than the width of the impulse response. And so we know, of course, that if there are 2 point targets, they're not going to be separated more than the impulse response. So if the Kramer-Out lower bound is bigger than that, then it really tells us that we don't have the ability to estimate or determine that there are 2 point targets and estimate their separation. Okay, so this is the classical Rayleigh criterion, and Rayleigh pointed out 150 years ago that as the separation between the 2 point targets goes to 0, it becomes very, very difficult to tell that there's 2 point targets and to estimate their separation. So people normally say that it's not really possible to estimate the position of the 2 point targets or the separation of the 2 point targets if their separation is less than the width of the impulse response. And that's what the units are on the horizontal axis. This is delta in units of the width of the Gaussian impulse response. Okay, let's compare this with an RSI. Now, as an RSI is going to have this a cosinusoidal pattern from each of the point sources. That's what we see here, what we've seen previously with an RSI. And a single point source produces a cosinusoidal pattern. And here we have the sum of the signals from each of the point sources. That can be integrated in this form, and we can set a relative phase so that this would be plus or minus, or it could actually be some other phase. But we're most interested in either nulling all the energy from the 2 point sources or trying to maximize it. And we could build that with the Mach-Zehnder geometry that we showed in the work of Nair and Tseng earlier. Now we can take the derivatives with respect to the unknown parameters, the mean position of the 2 point sources and their separation, and find the Fisher information matrix, and we get integrals that look like this. So now the joint mutual information is no longer necessarily 0, but it does happen that as delta goes to 0, that this term will go to 0. So we won't worry about it too much. We're most interested in what happens when delta is less than the width of the impulse response, so that can we estimate the separation between 2 point sources when their separation is less than the width of the impulse response. The Fisher information for the mean estimation of the point targets is not a lot different than what it would be for a focal system, so we won't worry about that. We're just going to worry about estimation of the separation between the 2 point targets. This is using numerical integration what that Fisher information looks like. The blue curve is the Fisher information for the measurement on the nulling arm, for the arm of the RSI, where we've tried to cancel the signal coming to minimize the output signal, and then most of that energy is going to go onto the other arm, and from the measurement on the arm that has most of the energy coming out, this is the mutual information. So that goes to 0 as delta goes to 0, but on the nulling arm, the Fisher information goes to a maximum when delta equals to 0. This green curve is the sum of the two, and what you're actually finding is if we look at the output of both arms of a Mach-Zehnder geometry of the RSI, then the Fisher information is actually constant for estimation of the unknown parameter delta, the separation of the 2 point targets. Now, this plot is assuming that x bar is equal to 0. So this is evaluating the mutual information numerically when the RSI is pointed exactly at the midpoint of the 2 arms. This plot is where we don't assume x bar is equal to 0. So so if x bar is relative to ours, say 0.2, then this is the Fisher information on the nulling arm, and this is the Fisher information on the arm that has most of the energy coming out of the RSI, and this is the sum of the Fisher information from both arms. And what we find here, for x bar equals 0, we're pointed directly at the midpoint of the 2 point targets. This goes to a maximum. If x bar is not equal to 0, the Fisher information is somewhat reduced. So we have a problem, of course, that we're looking at 2-point targets. We don't know necessarily exactly what the midpoint of the 2-point targets are. So we need to go through some kind of adaptive strategy. One of the things that's talked about in the textbook and simulated in this GitHub notebook is that we could use half of the photons that we're going to look at the target with to estimate the midpoint, and we would estimate that potentially using a focal imager instead of the RSI, or we could use the RSI as well. And then after we've estimated the midpoint, then we move the RSI to point at the midpoint and then estimate the separation between the 2-point targets. So this plot on the left compares the on the top, this is the Kramer-Hour lower bound for estimation of the separation of the 2-point targets using the Gaussian estimator, and then or the Gaussian measurement. And then this curve on the bottom is using Monte Carlo simulation for estimation of the separation between the 2-point targets as a function of the actual separation using this adaptive strategy. And and here I think the initially x bar was about 2.3, so it's off away from the origin, and then you spend half the photons to estimate that. Then you move the RSI to point at the estimated value of x bar, and then you make some measurements, and then we're going to use the maximum likelihood estimator to estimate this delta, the separation between the 2-point targets. It turns out that the maximum likelihood estimator is proportional to just the total number of photons measured by the RSI. If the separation is 0, the RSI would not measure any photons at all. So if you just integrate over the entire aperture all of the photons and properly normalize that, that gives you an estimate of the separation of the 2-point targets. If the separation was 0, it's possible to get a 0 measurement. If the separation is not 0, then this difference in between the total number of photons tells you what is the mean separation. And so that's something that's not possible, of course, with a focal system, because you're always going to measure a spot corresponding to the points. And so it's this ability to make the measurement close to 0 that makes it possible to separate the signal from the 2-point targets and really figure out that there is 2-point targets. And so here we're finding, this I think was for using 1 million photons overall in the measurement, and we get well less than 0.1% accuracy in estimation of delta, as delta gets to be very small. And so this shows us that we can go way beyond the estimate that Rayleigh thought a couple hundred years ago by using this interferometric measurement. And of course, it's much, much better than the work we had in our 2003 paper. So this shows that coherence measurement can enable us to get details that we can't get using conventional focal mechanisms, and we'll continue to come back to this theme in this chapter and the next chapter, and with an example later in the text to talk about how we can filter systems in optical imaging systems to improve SNR to get parameters that might otherwise be difficult. This gets again to the points that came up in lectures 10 and 11, where lecture 10 focused on parameter estimation, which is what we're doing here with the Rayleigh Criterion. We're estimating the separation and channel capacity. The channel capacity of a focal imaging system, as we'll see in some detail in the next chapter, is determined by the space bandwidth product, which is not improved really by coherence measurement. It's just a fundamental feature of an aperture. But real systems don't fill the channel capacity. The actual information in the system is sparse, and so here, because we're not looking at points densely filling the image, we just have these 2 points, and we're using the entire aperture with an RSI to estimate that separation. It turns out that this kind of nulling interferometry allows us to get better SNR for estimation of this single parameter than we would get with a conventional focal system. Next time, we're going to go into some detail about how people have tried to do this with focal systems rather than with an RSI. An RSI has many drawbacks for measuring complex imaging systems, so there's advantages when we look at real extended sources in dense fields in using a lens to filter out and find the information. We could imagine, of course, building an RSI in combination with the focal system by looking at a set of an area where there could be unresolved point sources, and then filtering it, and then analyzing it with an interferometer. But one can equivalently use mode sorting systems, and what we'll talk about in the next section is modal analysis of the coherence functions and how we can use that to similarly achieve sub-Rayleigh resolution of point targets. This is an example of a paper that's done this recently in looking at isolating exoplanets from star fields using modal filters. We'll talk a little bit about that in our next lecture.